Okay, so in this problem we have a 2 kilogram box. It's suspended from the end of a light vertical rope, and there's a time-dependent force is applied to the upper end of the rope, and the box moves up with a velocity magnitude that varies in time according to this equation. V of t is equal to 2 meters per second squared times t plus 0.6 meters per second. Well, the second one is second. Sorry, the 2 is 2 meters per second squared plus 0.6 meters per second cubed t squared. What is the tension in the rope when the velocity of the box is 9 meters per second? So, like I traditionally do, this is how you would quote unquote traditionally solve this if you were in like a physics class. I'm going to solve this more like graphically and obviously using calculus as well too. Calculus, algebra, geometry. Okay, so here's a setup. This problem I'm going to call it the jerk, and you'll see why in just a second. There is a box over here on the left, and it is being pulled. There's some force that's pulling it up. Okay. Now, it says that it is accelerating upwards. So if you wanted to, you could add an acceleration. You could say it's accelerating in the upward direction. Okay. There's still a force of gravity pulling it down, but the force that's going up is stronger than the force going down. Okay, and you see here is the, right here, this is the velocity, 2t plus 0.6 t squared. Now, when you say velocity equals 2t, well, that's in meters per second squared. So that's acceleration. So this right here is acceleration, which is fine. So it is accelerating, but there's this additional thing. It's 0.6 t squared, which is in meters per second cubed. This is called jerk. So this section over here is called jerk. That means, jerk means the acceleration right here. Sorry, acceleration is the change in velocity over time. Jerk is the change in acceleration over time. It's how much acceleration is changing. Okay, so what this is basically showing you is that not only, well, the acceleration is not constant because there is jerk is being applied to it, but also that the force is not constant, right? So if the acceleration is not constant, the force is not constant, because remember force is equal to mass times acceleration. So if the acceleration here is not constant, then the force is not constant, okay? So the force is changing over time because the acceleration is changing over time. And the reason the acceleration is changing over time is because there is jerk. There is jerk, okay? So the jerk is what's causing all the problems here. So what we want to know is we want to know what is the tension in this rope, right? So there's a rope right here. We want to know what's this tension in this rope at 9 seconds. Okay, great. So what we have here is we have a free body diagram. The little dot, of course, represents the box. And there are two forces acting upon it. Weight, or gravity, is pulling it down. And so the gravity times your mass is your weight in newtons. So here the weight was, the mass was 2. Gravity is 9.8. You multiply those two together, you get 19.6 newtons. So that is the force of gravity pulling this box down, 19.6 newtons. Great. So now I need to know what the tension is, and then we can figure out. What it really wants us to do is figure out the acceleration, because remember, acceleration is going up. So it's actually accelerating in this direction here. So what we're really going to do is we're going to find acceleration, and then once we find acceleration, then we'll get tension, okay? Okay, so this is where the fun starts. All right, so what we're going to do is just like normally, we're going to create a graph, and I'll create a velocity graph, and I'm going to put it right here, okay? This is a velocity as a function of time. Obviously, time is on the x-axis. And remember, this is velocity as a function of time is equal to 2t, which is your acceleration, plus 0.6 t squared. Remember this part here, this is the acceleration, this is the jerk. Great. So what does this thing look like if you plot it out? Well, it's going to look something like this, okay? Now, what it says is, what the problem says is that, so this function, this is this function. So the problem says, what is, well, I need to know what the acceleration is. I need to know what the acceleration is because if I know the acceleration, I can find the tension, right? So I need to find the acceleration. So let's do that. So what it says is that we want to know what the velocity is. Well, we want to know what the tension is at 9 meters when the velocity. Because if you look at the question, it says what's the tension when the velocity is 9 meters per second. Great. So I'm gonna go to the velocity over here. I'm gonna go 9 meters per second. Okay. So I know. So I have that. And I have the graph. But what am I missing here? Well, I'm missing the time. At what time will you get 9 meters per second of velocity? Okay, so let's do that. So obviously you have two functions, right? This is what I typically do. You have this function here, y equals 9, and then you have this other function here, y equals 2t plus 0.6t squared. Okay, so I have these two functions, and I'm just going to set them equal to each other, right? I'm just going to go 2t plus 0.6t squared. That's one function. And where does that equal 9? Where do these two functions intersect? So where does the blue one, which is this guy here, where does it intersect with the red one, which is this one right here? Okay, and all you have to do, of course, is just solve for t. And if you do that, you'll get t equals 2.55 seconds, 2.55 seconds, which is right here, 2.55 seconds. Great. So now we know that the box achieves 9 meters per second velocity at 2.55 seconds. Great. So now what I want to do is remember, I'm still looking for acceleration because acceleration will give me the force. Remember, because they're related. So I need to find acceleration. So how could I find acceleration? Well, I'm given v of t. Why don't I just remember, acceleration is just the change in velocity over time, right? So what I'll have to do is differentiate this velocity with respect to time, okay? Meaning I have to do dt, take the derivative of what? 2t plus 0.6 t squared. And if I do that, I'll get acceleration. So you'll end up here with 2t is just 2 plus 0.6 is 1.2 t. So this becomes this. So and then this is acceleration, right? This is now I have acceleration. Now what you could do is, if you wanted to, you could plot this out. You could say, okay, I have my velocity versus time. Now let's do acceleration versus time. So this is time, this is acceleration, and then this is in the y direction, right? This is in the y direction because we're only going up and down. Okay, so if you were to plot this guy, it looks like right here. So it starts at 2, right? Starts at 2. That's what the 2 is. That's your constant. And then 1.2t, that's just a straight line, okay? So this dot right here represents the initial acceleration, 2 meters per second squared, right? But the acceleration is changing, right? So this line right here is 1.2 t plus 2. And the slope here, the 1.2 t, that slope, that's actually jerk. So remember, jerk is the change in acceleration over time. So this part here, this part here is the jerk, and this part here is acceleration. The acceleration was initially 2, but of course it's changing over time. Now what I'd like to know is, I would like to know what is the acceleration. Remember, because the acceleration is changing, I want to know what it is at 2.55 seconds. So what I can do here is I can just do, put this down here somewhere like that. Go 2.55 seconds. Because at 2.55 seconds, it has achieved 9 meters per second velocity. So, okay, but what what's the acceleration at that time? Okay, so if I got 2.55, which is what I got from here. Now look for this guy, right? So all I have to do is, this is acceleration as a function of time is equal to 1.2 t plus 2. And all I have to do is pass in 2.55 into that function. And you'll get 5.06. You'll get 5, this equals 5.06 meters per second squared. That's this one, 5.06 meters per second squared. Great. So now I know the acceleration. So when the box is going 9 meters per second, when the box is moving at 9 meters per second velocity, it's also moving at 5.06 meters per second squared as far as acceleration is concerned. And it's doing this at 2.55 seconds after 0. Okay? Great. So now that I know that my acceleration, which is this one, let's do our free body diagram. So remember, this guy here, we have this, we have the tension going up, we have the weight going down. So what we can say here is the tension is the one on top, T, that's the one going up, so that we're going to count that as positive, and then minus the weight is pulling down on it, equals, so this is the sum of the forces in Y is equal to mass times acceleration. And so the sum of the forces in Y is tension is up, weight's down. It's equal to mass times acceleration. Mass times acceleration. Mass is 2. Acceleration, which we just got, which is here. Remember, it's time dependent. So this one's 5.06. 5.06. And then that equals, so then we have tension minus, and the weight, which we already had that up here, right? That's 19.6 newtons. 19.6 newtons. We'll just say 19.6. Okay. And then 2 times 5.06, that's a bad looking 5, is 10.12. This is 10.12. And then we're just going to add in 19.6. Add 19.6. We're just going to do a little algebra, right? And then we're going to do plus 19.6. Therefore, the tension equals 10.12 plus 19.6 equals 29.72 newtons. Okay, let's do that. Let's do this right here. So 29.72. Let's look at our answer here, and you can see here 29.7. So the tension, which is here, is 29.7. So we did get the right answer. Once again, just to recap, the force on this of the tension is not constant. The reason it's not constant is because the acceleration is not constant. And the reason the acceleration is not constant is because there is jerk. There is jerk. Okay? So the jerk is causing the acceleration not be constant, therefore the force is not constant. Great. And so just to recap, what I did is I created my velocity as a function of time. I knew the 9 meters per second. I knew this one. I knew this part. But then I had to figure out the 2.55, and all I did is I just set the velocity of time as a function of time, 2t plus 0.6 t squared. I set that equal to 9. I said, where did those intersect? Oh, 2.55 seconds. And then I differentiated the velocity function, created the acceleration function, because that's what I'm looking for really is acceleration. And then once I had the acceleration function, I passed in 2.55 seconds into the t parameter, and it popped out 5.06 as the acceleration. Once I had the acceleration, then basically I'm done. Then I just do F equals ma. So this is the change in velocity in y equals is it ma. My tension minus my weight, that's the sum of the forces, is your mass times acceleration, the acceleration I just got, and I did some simple algebra, and I got 29.72. So anyway, once again, you could have done this problem the traditional way, but sorry about that. But I, kind of like this way better. It's more intuitive, like you can graphically see what's happening. And of course, if you're pretty confident in your calculus abilities, you can easily move around this space, okay, instead of having to rely on a wall, as I've usually said, a wall of equations. All right, hope you enjoyed it. That's it.